continue our discussion, and what I want to do now is to show you an explicit example of matching. We're going to do an explicit calculation in the simplest possible situation, one in which both the UV theory and the infrared theory are weakly coupled. Okay, so consider a full theory which is describing a Dirac fermion, which I will denote with psi, and a real scalar phi. So you have the kinetic term and a mass for the fermion. The fermion will be our heavy particle. Then there is a kinetic term for our scalar mass. Let's call it m phi. And then I will add also a quartic interaction for the scalar. And it's possible to write a Yukawa interaction between the fermion and the scalar. Now, in writing these interactions, I'm assuming that the theory is invariant under parity transformation, which I can call P, under which psi goes into, well, some intrinsic parity, which I don't need to specify, in fact, because it's irrelevant for this discussion. And phi is odd, so it goes to minus phi. Okay, so I'm postulating in writing the UV theory that the theory is invariant under this parity transformation, which in particular forbids cubic term for the scalar, and then fixes the form of the interaction, of the Yukawa interaction, to be one involving gamma 5. Okay, so psi is a pseudoscalar, and it must couple in this way. So this is the full theory. And I'm taking the limit in which m psi, okay, is much larger than m phi. Okay, so this is my assumption. So I want to integrate out the scalar psi and match to an effective theory. The effective theory will be one containing only the light degree of freedom, which is a scalar. So there will be, again, kinetic term, mass term, quartic interaction, plus a series of higher dimensional operators, in particular dimension 6, dimension 8, plus blah, blah. Now, you can easily see that the fact that the theory is invariant under this parity transformation, well, both the UV theory and also the effective field theory, implies that there are no possible operators of dimension 5, okay, and in fact dimension 7 as well, because that would imply an odd number of scalar fields, and those are not generated because they are breaking parity invariance. Okay, so we had to identify which are the leading operators of dimension 6. We will neglect dimension 8 operators, and then match. Okay, match the two theories. Now, notice that in principle, actually not only in principle, but in practice, this mass parameter and this coupling self-quartic interaction in the effective theory are different, have values which are different from the corresponding parameters in the UV theory. So I will denote them with tildes. Okay, I hope I will keep track of these tildes. If I forget, well, you know that the parameters in the effective theory, okay, are those with tildes, and in general are different from the ones that appear here. And in fact, we will derive the expression of lambda tilde as a function of lambda. So what are the dimension 6 operators? Well, you list all possible operators that have the right quantum numbers. They have to be even with respect to these parity invariants. So for example, there will be one operator. Actually, let's organize the operators according to the number of derivatives, okay? This is the correct thing to do. So with 0 derivatives, obviously there is only 5 to the 6th, okay? One derivative is not Lorentz invariant, so 2 derivatives. At the level of 2 derivatives, you can write a bunch of operators. For example, you can write phi d mu phi square. You can write, actually, let me write them here, okay? 2 derivatives. Then there is, for example, phi cube box phi. There is phi square d mu phi square, and other possible combinations. Okay. Now, what I at this point I can use is the equations of motions. Equations of motion, which can help me to reduce the number of operators. And now the result of this simplification is that the only 2 necessary operators, I mean those which are not redundant, are phi to the 6th and one of these operators. For example, phi cube box phi can be rewritten by using the equations of motion, which I can write here, just to remind you. So equations of motion using L4, okay, are box phi equal to minus m tilde phi square phi minus lambda tilde over 3 factorial phi cube. Okay, so if I use these equations of motion here, then, in fact, as we already saw last time, I get operators which are already present in the Lagrangian, because there is m tilde phi squared phi to the 4th minus lambda over 3 phi to the 6th. Okay. Similarly, for the second operator, I can actually, sorry, this is the same as this. So you can have, for example, d mu phi square, d mu phi square. Okay, this is obviously related to the others because you integrate and you get 4 d mu phi square. So you can have phi d mu phi cube, okay? But then you integrate by parts, okay? And up to total derivatives, again, you can use, for example, equations of motion, and then everything in this list, okay, eventually can be rewritten in terms of the first operator and phi to the 6th, okay? Well, this I leave you as an exercise. So basically, the dimension 6 Lagrangian is, at this point, just made of 2 terms. The first with a coefficient which I will call C, and the second term with a coefficient which I will call C6, plus higher dimensional operators. So the goal of matching is to determine the value of these 2 operators here, these 2 effective coefficients here, okay? And how do we do? Well, we use the definition of matching, the recipe for performing the matching involving green functions, the second approach that we were discussing yesterday. Okay, so I need to identify the green functions which allow me, once computed both in the UV theory and in the effective theory, allow me to extract these two coefficients. You understand clearly that the green function which allows me to extract the coefficient C is a 4-point green function, okay? And instead for in order to extract C6, I will need a 6-point green function. Okay. So C6, I leave it to you as an exercise, while I'm now going to extract C. So, for example, okay, so this is so this gives me the coefficient C, while so this is the fermion psi and the green function in the UV theory, okay? While in the effective theory, this operator here will give me an effective interaction among 4 phi's. Okay, so comparing these two, I will extract the coefficient C. Similarly, okay, if I consider a 6-point function, okay, then I compare it with an effective coefficient, with an effective vertex involving 6 scalar fields, I get C6. Okay, so what we are going to do is to focus on this part, and this I can leave it to you as an exercise. Okay, but it goes along exactly the same steps as for this. So we want to do the calculation both in the UV theory and the effective theory. Let's start to do the calculation in the effective theory. Okay, so we want to compute the 4-point function. So the 4-point function has at one loop, at 3 level, has 2 contributions. Okay, the contribution coming from the normalizable quartic interaction, self-interaction, and then the contribution from the effective vertex. Okay, so these are phi fields, of course. So the amplitude in effective field theory has, well, the first term has a value, gives a contribution, first diagram gives a contribution minus I lambda tilde, and that's it, okay? Plus the contribution from the second diagram, which can be written as, well, at this point there is some coefficients which I leave to you to compute. So this is 2ic plus the sum of the squares of the momenta, which are defined in this way. So here P1 and P2 are incoming momenta, and P3, P4 are outgoing momenta. Okay, so I define momenta in this way. The fact that you reconstruct the sum of the squares is not completely obvious at the beginning, because the operator involves products of any two of these momenta. So P1.P2, P1.P3. So eventually, exercise, once you take into account all possible weak contractions, and you take into account all possible contributions, you reconstruct this form here. Okay, so far so good. And at this point, I need to compute the same green function in the full theory. Okay, so again, there is a contribution from the three-level coupling, and then there are 3 possible topologies for the one-loop contribution. Okay, so again, in the loop, you have a virtual exchange of the fermion. Again, the momenta are defined in the same way. So this is the first diagram. Let me call it diagram A. Okay. Then there is another possible weak contraction where P1 and P2 are the same, but P3 and P4 are exchanged. So this is a cross diagram where T and U are exchanged, okay, with the same rooting of internal momenta. And let me call this B. And then there is another diagram, another topology, okay, where you exchange P1 with P3, okay, with the same rooting. I think I want to define the rooting in a different way, sorry, just to have it the same as in my notes, okay? So I want to have it this way.
Roberto, there is a question.
Sure, just a second, let me finish here.
Yes.
And this is C. Please.
Hi, thanks. So I am a little bit confused about the effectiveness of using an EFT if we have to do the calculation in the UV theory anyway in order to get the full EFT Lagrangian.
You mean the calculation of the green functions?
Mm-hmm.
Yeah, I mean, that's the matching, right? So you know the UV theory. This is an example in which you know the full theory. You know the form of the effective field theory you can guess without any calculation, just based on symmetries. Of course, you have to make an assumption. What are the symmetries in the infrared? Okay, and that's upon you. Okay, but you know you have enough experimental information to tell whether, for example, phi is a pseudoscalar and the interaction of phi respect parity. Okay, so once all this information about the low energy dynamics is known, then I can tell you all possible operators that can appear at a certain level. For example, at the leading order here in the expansion, which is dimension 6. Okay. At this point, I'm left with C and C6, which are the only two unknowns. To fix these, the value of these coefficients, I necessarily have to do the calculation in the UV theory. There is no other way, of course. Am I addressing your question, or?
Yes, that makes sense. I guess really my question is when you don't know the UV theory, I guess how does this work? Does it still work?
Of course. Yeah, we will discuss this later. Okay, we will see. Of course, in that case, you don't know. There's no way to compute C and C6. Okay, right. So either you make estimates of these coefficients, and we will discuss how to do them, or you define, you focus on observables which do not depend on C and C6. Okay, and that's possible. Or the third option, as we will discuss, is to extract C and C6 from data. That's the other possibility. But this is it's for later. Okay, now let me focus on a situation in which you know the UV theory, okay, and you want to do matching. So these are situations which are really, I mean, of importance in actual physical situations. For example, if you want to compute precisely the rate of decay of heavy, sorry, not heavy, but mesons like, for example, the kaons, or even heavy mesons like B mesons, then what you do is so these decays occur through electroweak effects, okay? And then what you do, if you want to do precise calculations, and the reason why you need to go through effective field theories will be clear later, you integrate out the W and the Z at the electroweak scale, okay? You match the full theory to an effective theory, which is basically a theory with 4 fermion interactions, okay? And you use that effective theory to do your calculations, okay? This is actually give you a better theoretical precision, again, for reasons that will be clear later. So in that case, you do know the UV theory, and you need to do the matching. Okay, so this is a prototype for this kind of situations of which occur in real life. Okay.
So Roberto, we have other questions.
Please.
Hi. Why we don't put also a constant in front of the kinetic term in the effective field theory Lagrangian?
Yeah, you can, but you can. I've normalized canonically the field. Okay.
Okay, so in general, the field phi in the effective field theory Lagrangian is not the same in the full.
Correct. That's a good observation. So even the field is not the same, okay, and its normalization will be different. Now you're right that in doing the matching, okay, in general the matching is most naturally done in a basis in which the kinetic term is not normalized canonically. Okay, so here, if you want, I'm normalizing canonically. I'm choosing this basis to normalize canonically the field. Okay, so in general, you can remove it.
Okay, thanks.
And in fact, there is also another thing which comes to my mind, but I will discuss it later. So there are other loop diagrams which you might consider contributing to actually one loop diagram plus crossed, which is contributing to the 4-point function. And this diagram is, let me write it here. It appears both in the UV and in the infrared theory. It's simply a loop diagram, okay? The usual loop diagram, which it's present in phi to the 4th, where these interactions are normalizable interactions. Okay, so this diagram I do not need. It's present both in the UV and the infrared, and it's the same. Okay, so at the level of precision that I am interested in, where lambda tilde, okay, are the same. So these two things are really the same, and I don't need to introduce it, okay, in the matching, to take into account in the matching to derive the value of C. Okay, so this diagram is not going to play a role in the matching, but I will tell you a few words about this later. Okay.
There is also another question. You have a serious one. So.
Please.
Okay, I wanted to ask why we go to the one loop level in the UV theory and we just stop at the 3 level in the effective field theory. How we decide that? Well,
okay, at the 3 level in the UV theory, there is nothing. Okay, there is no interaction among. I mean, there is no contribution to the coefficient C. So I need necessarily to go at one loop. Okay, and that's the leading contribution. And again, in the effective field theory, okay, I could do loops, okay, involving the effective interaction. Okay, but this will be higher order. I will discuss about this later, okay? But I'm just considering the leading effects both in the UV and in the effective field theory, okay? So and this will give me the first term in the matching. Then of course I can consider next to leading order corrections, and I will discuss about them. But okay.
Okay, thank you.
I'm doing an systematic expansion, so I'm considering just the leading effects. Okay, so let me compute
we
this.
have also a question on the notation in the chat. Is if A is the green function, so the A you wrote there. The question is A the green function?
No, A is the amplitude. Capital A is the amplitude. Okay. So if you want, yes, is the calculation of the green function. Yeah, is the amplitude of shell. Yes, it's the 4-point green function. Okay. Yeah, the answer, if you want, is yes. So it's just the Feynman amplitude, but it's the same. Okay, in momentum space. Okay. Very good. So the result, okay, in the full theory, again, for the amplitude or the green function, is minus I lambda plus, actually, now let me write in this way, minus 2 y to the fourth times a plus ab plus ac. So the minus comes from the fact that there is a fermion loop. Okay. The coefficient phi to the fourth is nothing else than the combinatorial factor that you have, because you are working at fourth order in perturbation theory. So you have I times y to the fourth, okay, coming from the interaction which I just erased. That's the Yukawa interaction. Then you're working at fourth order in perturbation theory, so you have I to the fourth divided by 4 factorial. And then there is a combinatorial factor which counts how many weak contractions you have. Okay, so for example, if you want to attach the first external leg to the vertices, you have 4 possibilities. And once you have attached the first leg, then you try to attach the second leg. At this point, there are 3 vertices at your disposal, okay? And the first and the last, and the third leg, okay, has again 2 possibilities, and then there is only 1 possibility for the fourth leg. So eventually, okay, this is just y to the fourth, which I put here. And then still, okay, once you have attached the external legs to the vertices, then you have different, actually 6 possibilities to close to attach the vertices together to form a connected diagram. Okay, and they are the same in pairs. Okay, so there are 2 topologies which are equivalent to A, 2 topologies which are equivalent to B, and 2 which are equivalent to C. So this is, okay, these 2 comes from the multiplicity number of topologies, if you want, of contractions of equivalent contractions. Everything I said you should check, okay? So also because there might be mistakes. So you need really to check my calculations. So let me start with the calculation of the first diagram. Now, this diagram involves an integral. Okay, let me call k. Sorry, unfortunately, I didn't write the internal. Let me write here. Okay, the internal momenta. So I choose to call the internal momentum k. Okay, so remember this moment. The external momentum is P1. This is P2. P3, P4. Okay, so the momentum flowing here will be P1 plus K. Okay, here you will have P1, P2 plus K. And here there will be P3 plus K. Okay. So this integral is an integral over K. And there is a trace. Each vertex has a gamma 5. Okay. And then you have 4 propagators. Okay, each propagator has an I in the numerator, but since there are 4, I can forget. So there will be kappa slash plus P1 slash minus M psi. I'm starting from here. Okay. Then there will be gamma 5, 1 over K slash minus M psi, gamma 5, 1 over K slash plus P3 slash minus M psi, gamma 5, 1 over K slash plus P1 slash plus P2 slash minus M psi. Okay. Now, computing this integral with generic P1, P2, P3, and P4 is complicated, okay? So we need to make a simplification. And the simplification comes because I can match the two green functions. I mean, the one in effective action, which is already computed and it's valid for any choice of a standard momenta. I can do this matching for any specific kinematic point, okay? So I can choose, in other words, I can choose the values of the external momenta as I want. And I will choose the following kinematic point for simplicity, for convenience. I will choose P1 equal to minus P2 equal to P, and P3 equal to P4 equal to 0. Okay, so that's just for convenience. So in other words, there is some momentum P which enters into the first leg, okay, and goes out on the second leg, but the P3 and P4 are 0. So under the choice of these kinematics, this integral simplifies, okay, and you see at this point I'm left with only one, outside one external momentum. So this gamma 5, 1 over k slash plus p slash minus m psi. Okay. And now I can move the gamma 5s. For example, I can bring these, okay, on the left of this factor, okay, and this will change the sign of kappa slash, okay, and then it annihilates with the other gamma 5, and then these two again can annihilate by changing again the sign here of kappa slash. So eventually I get 1 over kappa slash plus p slash minus m psi, 1 over kappa slash plus m psi. This is this factor, okay? I'm factorizing two factors of minus 1, okay? One coming from here, one coming from here. And then these two factors, okay, one becomes kappa slash plus m psi, and the other is kappa slash minus m psi. So putting them together, I get 1 over k squared minus m psi squared. Okay, so these are coming from the multiplication of these two last factors. So here, what do I need? Well, I don't need this calculation for as a function as a function of p. I just need the expansion for p going to 0, right? Because I need the leading term, sorry, the p to the 0 term, which will be useful and contribute to lambda tilde, okay, p to the 0, and then p squared, which will contribute to c. Then terms of order p to the 4th, p to the 6th, etc. are not needed because they're used in the matching of higher dimensional operators. Okay, so what I'm saying is that I just need to expand, Fourier expand, sorry, Taylor expand the first term here. Okay, that's exactly the Taylor expansion that we were discussing in the first lecture. Okay, so let me Taylor expand this first factor in the trace. That's easy. Okay, so I have 1 over k slash plus p slash minus m psi. This is what? This is 1 over k slash minus m psi plus p mu, the derivative with respect to p mu of 1 over k slash plus p slash minus m psi computed at p equal to 0, okay, plus 1/2 p mu p nu, the second derivative p mu, actually let's do p nu 1 over kappa slash plus p slash minus m psi computed at p equal to 0 plus orders p to the 4th. Okay, and these, okay, now we need to compute these derivatives, but first notice that once you plug this into the integral, then the term which is linear in p, eventually the integral, okay, which is coming from this term, will vanish, because you cannot have a term in the green function in the amplitude which is linear in p mu. It will not be Lorentz invariant. Okay, you will not be able to match this index, to contract this index with some tensor. So necessarily this term will give you, once you put it in the integrand, will give you an integral which vanishes because it will be linear in k. Okay, sorry, linear. Proportional to odd factors of k, which eventually will vanish. Okay, so this term, in other words, we can forget. Okay, is not giving to us anything interesting. So let's focus on this. Okay, let me give you the expression for these two terms. Anyway, so I will give you also the first, so you're able to do some check. But again, the first term is not important. So this is minus p mu minus gamma mu. Actually, I will not give it to you, okay? So I'll give you only this, just to be more concise. P mu 1 over kappa slash plus p m psi at p equal to 0. So this is equal to p mu p nu, which multiplies minus 2 gamma mu kappa nu plus 2 gamma nu kappa mu plus 2 eta mu nu kappa slash plus psi over k squared minus m psi squared all squared plus 8 k mu k nu kappa slash minus, actually plus m psi k squared minus m psi squared cube. Okay. So basically, you use this into here. Okay. You write the Taylor expansion in the trace, and then you do a little bit of algebra. Okay. And also you use the fact that well, first you use the fact that terms odd in K vanish. Okay, I'm using dimreg, by the way. I'm going to use dimreg, okay, because the diagram will diverge. Okay, in fact, you see that there is a logarithmic divergence. Okay, so I had to use dimreg. So all terms which are odd in the number in the internal momenta vanish, and I can drop them. And then the second observation is that in dimreg you have that the integral in the whatever d4, let's say d4k, okay, d4 kappa of k mu, any function of kappa square, okay, is a eta mu nu. Sorry, it's equal to eta mu nu. Sorry, is equal to eta mu nu over 4 the integral d4k of f of k squared. Okay, well, this is simply true because these are regularized integrals, so you act with eta mu nu, you contract, and you get, you can verify this identity. Okay, so plugging this into the trace, okay, the Taylor expansion, dropping terms which are odd in k, and using this, this identity, after a bit of algebra, leads you to the result which I'm going to write. Let me write it here because I want to keep this form. I want to keep this expression. Okay. You plug into here and you get that.
Roberto?
Yes.
There is a question about the expansion you wrote upstairs.
Please.
So the minus sign inside the square brackets, does it refer to the 2 or to the whole?
Yeah, sorry, it's to the in front of the whole thing. Sorry, it was a bit unclear. Yes, it's in front of the whole thing. Okay.
I guess you're also missing a factor k square in the equation you wrote, the last equation you wrote, the one with the eta mu nu.
Yeah, sorry, that's true. Here, thanks. Very good. Okay. Let me check if there is anything else. -2. Sorry. +2 eta mu nu. Okay, so everything should be okay. And at this point, okay, if you perform a little bit of algebra, you'll find the following. You'll find that, let me jump, okay, to the final expression. A of A is equal to 4 integral d4k over 2 pi to the 4th 1 over k squared minus m psi squared squared. That's the term p to the 0 plus d4k over 2 pi to the 4th 2p squared, which multiplies -1 over k squared minus m psi squared cubed plus m psi squared divided by k squared minus m psi squared to the 4th plus orders p to the 4th. Okay? Okay, very good. So at this point, you need to compute these integrals in dim-reg. Okay? And now, of course, the term which is proportional to p squared by simple inspection is a finite integral. But the first one is log divergent. Okay? So you need to resort to dimensional regularization. And in general, okay, sorry, not in general, but in dimensional regularization, you can derive the following formula, following identity. Okay, so mu is the subtraction normalization scale in dimensional regularization. So mu to the 4 minus d, where d is the number of dimensions. Integral in the d k over 2 pi to the d of 1 over k squared minus m to the n okay, to some power n. This is equal to I minus 1 to the n divided by 2 pi to the d, mu 4 minus d, pi d halves divided by gamma n minus d divided by 2, m square to the d divided by 2 minus n. Okay? So in particular, this gives for n equal to 2, which is the case for the first integral, it gives you the following. It gives you mu to the 4 minus d. Well, it gives you, so let's call this I of n, okay? Then it gives you I of 2 equal to I divided by 16 pi squared, which multiplies 2 over epsilon, where epsilon is defined, let me write it here. So d is 4 minus epsilon, okay, as usual, minus gamma e plus log of 4 pi plus log of mu squared divided by m squared plus order epsilon, which eventually vanish and are not important. Okay, so you need to use this formula to evaluate the first integral. While for the second integral, you just use this general expression with n equal to either 3 or 4, okay? Okay, that's easy. Okay, so eventually, if you do this, if you use these formulas in DIMREG, then you get our final expression, which is the following. I divided by 4 pi squared, which multiplies 2 epsilon minus gamma e plus log of 4 pi plus log of mu squared divided by m psi squared. Okay. Plus four over 3i p squared over m psi squared, 1 over 16 pi squared, plus order p to the fourth. Now, of course, here I've not introduced, and I should have introduced counter terms to kill this divergence. Okay, but that's not a problem because it's easily done. Okay? And in fact, what you can do is to choose the usual minimal subtraction, for example, ms bar, where the counter term kills exactly this parenthesis here. Okay, in the ms bar scheme, so this term here is canceled. How do you cancel it? Well, okay, you can introduce counter terms, and the counter terms, again, we are working in the full theory. Okay, so in the full theory is a normalizable theory, so there is no complication. How do you do? There is a divergence here. It's a logarithmic divergence. It has to be canceled by a counter term. What is the counter term? Well, it's the quartic coupling of the scalar. Okay, nothing mysterious. So the quartic coupling of the scalar. Let me write it. Let me write it here. Okay. Let me write it here. Okay. So L counter term, okay, in the full theory will include a term which has exactly the form of the quartic coupling. So it's lambda over 4 factorial, okay. And well, it arises from the fact that the Baire term, which I wrote, okay, where everything is bare, so both lambda and the field, will get will get multiplied by z factors. So in particular, there is a z phi to the square if you define phi equal to phi renormalized, okay, times z phi to the 1/2. Okay, so this is, if you want, this is the bare field. Okay, let's call it phi 0. Okay, and then you can define lambda 0 to be z lambda times lambda. Okay, and then here you will get the z lambda. Now, if you expand, let's see where I can write. If you expand these z lambda and z phi, okay, and isolate the content terms, in particular, you can write, let me write here, z lambda to be defined as 1 plus delta lambda, okay, and z phi I define to be 1 plus delta phi, okay. Then this term becomes lambda over 4 pi, 4 factorial, sorry, phi to the 4th, okay, 1 plus delta lambda plus 2 delta phi. Okay, so the first term, the one in the parentheses is already written, and it gives me this result. Okay, in fact, it gives me the term, sorry, here I forgot to add the three-level diagram. I only wrote, because this is only A, sorry. Yeah. I should have written the full expression. But I'll do it later, okay? I'll do it later because I had to sum also the diagram B and the diagram C, okay? What I want to say is that these are the content terms, okay? And these content terms will add here contribution, okay? Which will cancel eventually this divergence. Let me put these all together at the end, because in fact, this is not the full amplitude, is just the contribution of a diagram. So let me rewrite here orders p to the 4th. Okay, and let's keep in mind that these content terms eventually will cancel the divergence. Okay, so summarizing, I've done the calculation of the first diagram. Okay, I'm finding this result, which you should check. There is a first term which is of order p to the 0. And this, of course, will be matched by the term going like lambda tilde in the effective theory. And then there is a term which goes like p squared, of course, divided by the mass of the fermion square. And that will be matched with the coefficient c, with the term proportional to c. Now, however, this is only one diagram, so there are the two diagrams. And let me give you the expression also for these other two diagrams. First of all, you see from this equation here that the diagram B, where you exchange P3 with P4, is exactly equal to diagram 1, to diagram A, with our choice of kinematics, because both P3 and P4 are 0. So diagram B does not need to be computed because it's equal to diagram A. Okay, AB is equal to AA, at least with our choice of kinematics. Diagram C, instead, needs to be computed. I don't want to make it too long. I'll give you the result, and then you will check it. So diagram B, diagram C has this expression. AC is equal to the term which goes like p to the 0 is the same as in A. Okay, so I over 4 pi squared, which multiplies 2 over epsilon plus minus gamma E plus log of 4 pi plus log of mu squared over m psi squared. And then there is the following expression, plus 2/3 I p squared over m psi squared plus orders p to the fourth. Okay. So basically, yeah, this term is and I'm forgetting, I think 16 pi squared. Okay. I over 16 pi squared p squared over m psi squared. It's a factor 2 smaller than the second term in the expression for AA. Okay, at this point you need to sum, okay, AA, AB, and AC, okay, and use it over there in the expression on the top, and then you get the final expression for A full. Okay, so A full is minus I lambda. And then at this point, let me do also renormalization on the fly. So I will add the counter terms. I choose minimal subtraction, and minimal subtraction is just the removal, the minimal removal of divergences, which means that you just have to drop these parentheses here. Okay, so I don't write the counter terms. I already do the cancellation of divergences. So what I get is minus I lambda. Then there is minus so 3 over 2 pi square y to the fourth 3i y to the fourth log of mu square over m psi squared minus 2i, actually I, y to the fourth divided by 8 pi squared. Sorry. I need to make a little algebra on the fly. So this is actually 5 divided by 12 pi square, 5i divided by 12 pi square, y to the fourth p squared divided by m psi squared plus order p to the fourth. Okay, so that's the final expression for the 4-point function with the choice of kinematics that we did for convenience, okay, in the full theory after renormalization. Okay, and now you have to compare this with this, okay, with the expression, and this is the matching. Okay, and matching tells you that you need to choose the value of C and also lambda tilde in such a way, that you reproduce the expression in the full theory. And then if you do this, then you get that lambda tilde is equal to lambda plus 3 divided by 2 pi squared y to the fourth log of mu squared over m psi squared. And then C is equal to minus 5/3 y to the fourth divided by 16 pi squared 1 over m psi squared. Okay, so this is the result of matching. Is there any question so far?
Yeah, there is one.
Please.
Hello, can you elaborate more on the matching condition like P1, P2, P3, P4? Does different choices of external momentum give you the same answer?
Yes. Okay, so that's our freedom to choose the kinematics, because you need to do the matching, okay, for off-shelf green functions. Okay, so different choices will give you the same, will give you the same answer basically, because what you want to match, in fact, are the Lagrangian, in a sense, no? The two Lagrangians. So you have the Lagrangian in the full theory, the Lagrangian in the effective theory, okay? And then with these Lagrangians, you compute, or if you want, instead of the Lagrangians, you can think of matching the generating functionals, okay? As we did right yesterday. So yes, so the answer is yes. So if you want, this result should not depend on the choice of kinematics.
And also the on-shell and off-shell matching. Does on-shell and off-shell has difference in those
Yes.
problems?
So yeah. So this we were discussing at the end yesterday. Remember? So the off-shell matching gives you a value of the coefficients, okay, in a certain basis. But then you can use the equations of motion to change basis. For example, instead of writing your Lagrangian in terms of the operator phi d mu phi squared, no? So what is this matching saying? It's saying that the coefficient of this operator has this value, okay, and the coefficient of other operators, for example, no, the coefficient, let's call it C prime for phi box phi cube, okay, this is equal to 0, no, in the basis we are chosen, and also the coefficient of the other operators. But if I do a field redefinition, then I can change, I can reshuffle things, and I go into a basis where the value of the coefficient is different, okay? So the value of the coefficients is basis dependent if you match off-shell green functions, okay? Because you're matching green functions and you're not matching observables. So in a sense, it might seem a paradox, but actually the point is the following, that observables allow you to fix only a subset, if you want, a smaller number of linear combinations of coefficients, okay, smaller than the total number of coefficients. So that is the only unambiguous information which comes from observables. But the coefficients are more than this number of constraints. So you can choose different bases in which the coefficients have individually different values. But of course, the physical linear combinations are kept fixed. Okay?
Thank you.
Okay. Yeah. So with our choice, okay, of basis, there is only one operator, and this operator has this value. Any other question?
Hello.
Hi.
We ignored the set of diagrams where scalar runs in the loop. If we took them into account, it would have contributed in this matching result. Maybe
not a disorder, not a disorder, however.
I say, but like C would get a contribution at lambda square, right?
C would get a contribution as a, no, because you see, it's exactly the same, no? It's exactly the same diagram. So let me comment about this, okay? And in fact, I was about to do it, okay? So before doing that, let me make a few, let me put it in a broader discussion. Okay, the broader discussion is about the structure, okay, of these matching expressions. So the first observation is that there is a log here of mu squared divided by m psi squared. So there is a dependence in the matching expressions on the heavy mass, which is non-analytic. Okay, because you see, it's a logarithmic dependence, so it's a non-analytic dependence. Obviously, this non-analytic dependence on the parameter, no, on the mass, on the heavy mass, is inherited from the UV theory, because this parameter does not appear in the effective theory other than, okay, in the value of the coefficients. It's not a parameter of the effective theory, m psi. Okay, since the full result has this non-analytic dependence on m psi, necessarily the matching conditions, the matching expressions must capture entirely this non-analytic dependence of the full result. Okay, that's trivial. What about the dependence on p? Okay, on p squared. Well, you see that in this case, okay, for the diagrams that I computed, actually the dependence is analytic. It's only the level in which we are working is only a p squared dependence. Okay. However, if I add also the other diagram, okay, this diagram here that you were asking about, this diagram instead will have a dependence. It will go like lambda square, okay, over 16 pi squared times some function of p square over m phi square, for example, in the full theory, okay, and then p square, and if you want, yeah, p squared over mu square. Okay, there are three-dimensional full parameters, okay, which appear here: the momentum, the normalization scale, and the mass of the scalar. Okay, it's a loop of scalars, so there are no other parameters. And since this, sorry, and I had to put here, yeah, for this in this particular case, the overall dimensionality of the Green function is 0, because it's a 4-point Green function in 4 dimensions. Okay, so it's just an adimensional function, and it depends on 3-dimensional full parameters, so it can only be a function of these 2 ratios. Okay, and in general, the dependence of p square, the dependence of this function on these 2 arguments, on its arguments, will be complicated and nonlinear. Okay, so if you really want to compute the full expression in the full theory, you should also add this term. Okay, but then there will be an equal contribution also here in the effective theory, which has exactly the same form, but you just have to replace lambda with lambda tilde and m phi with m phi tilde. Okay, the same. So if you work at leading order, okay, and you forget about this, at leading order, you see that lambda tilde are the same. Okay, so at the level at which we are working, where this is already a correction, there will be no change, okay, in our matching conditions. But the most important thing is not about this detail. The important thing is that the full result, the expressions of both A full and A effective do have some nonlinear dependence on the momentum, okay, and also a nonlinear dependence on the parameters of the effective theory, okay, in particular the mass of the light guy. However, this nonlinear dependence cancels out in the matching, so it does not appear in the matching equations, simply because it is the same both in the UV and in the infrared by construction. Okay, by construction, because the effective theory is constructed, is defined exactly to reproduce the low energy behavior of the full theory. So every nonlinear dependence on the low energy parameters, momenta and masses, must be the same in the 2 theories, and it must cancel out in the matching. So if you found a log of m phi, that would be a bad sign. Okay, so in the matching condition, there cannot be any log of m phi, but there will be, and there can be, and there will be a log of m psi. Okay, because in fact, this nonlinear dependence on the coefficients of the high energy theory, the UV theory, can appear and must be captured by the matching expressions. Okay, in fact, the nonlinearities here have to do with also are connected with the infrared divergences. For example, okay, if you go to a limit in which p square, okay, is much larger than or if you want let's write it in this way, m phi, okay, is much smaller than p. Okay, in the limit in which the mass here, the scalar, is becoming very small, you see that here there is an infrared divergence, right, in this loop integral, and this turns into a log of m phi over mu. Okay, in the presence of a log of m phi over mu square. So you see that the non-analytic dependence of the result on the parameter of the low energy theory, the mass, the light mass, is connected with the presence of infrared divergences. And again, infrared divergences must be the same both in the UV theory and in the effective theory, and they must cancel here in the matching. Okay, this is very important. Okay, and it's the first observation I would like to do. Now, at this order, okay, there is no log, no non-analytic dependence in the value of C. And in particular, there is no term, okay, which involves logs of m psi over m phi. However, this is only a consequence of the fact that I'm working at one loop level. Okay, and now I'll sketch what happens at two loop levels without doing calculations, however, but I'll tell you the structure of the result. And I'll show you that also these terms appear in general. Now, the presence of the logs is important because, for example, the fact that you have a log of mu over m psi tells you that what is a good choice for mu, right? Because mu is arbitrary. No? It's a normalization scale, so you can choose it in the way you want. And in particular, it has to be chosen in such a way that perturbation theory, which I'm using to do matching, to extract these equations, is valid, no? is okay. Now, the problem is that if I choose mu much, much smaller than m psi, then this log can become large and can, in principle, invalidate perturbation theory because y to the fourth times the log might become of order 1 despite the fact that y is smaller than 1. Okay, so this would invalidate perturbation theory because formally you're expanding in y to the y squared divided by 16 pi squared, but in practice there are also logarithms which are appearing, and if these logarithms are large, then perturbation theory might be invalidated, and it will be invalidated. So this log is a signal of the fact that a good choice in order to keep everything perturbative is mu of order m psi. Okay, and this is what you have to do in order to have perturbation theory. Okay, to have perturbativity in the matching. Okay. Now, however, as now we are going to see, if you go at two loops, then logs of m psi over m phi will appear. And these are even more problematic because at this point you cannot dial. I mean, these are values of masses that you are given. Okay, so this cannot be made small. I mean, this ratio cannot be of order 1 certainly, because otherwise you cannot build any effective theory at all. So this ratio is necessarily large, and the log can be very large. So how to deal with these logs, it's what I want to discuss now, and the resolution to this problem is using the normalization group. Okay, but first let me sketch the form of the two-loop result, and let's see how these logs will appear. Okay. I think I have only 5 minutes, so let me.
Yes, Roberto. Remember that in something like 5 minutes we need to.
Yes.
Close.
Let me sketch this. This is simple. Okay, I don't need to do any complicated calculation, so I need to sketch this. The form at two loops, or the form of the green function at two loops, and then make a comment. Then I will start again tomorrow. I will resume from this point, but I want to write it now, so you have more time to think about it. So if you go at two loops, then in the full theory, okay, then you will have diagrams. So these are the one loop plus cross. And then you have also diagrams of this kind. Okay, so this is the fermion, and this is the loop of scalars. Okay. Now, the amplitude in the full theory at this point will how will it go? Well, it will go like there will be the usual term at tree level. Okay, there will be the usual term at one loop. Okay, and actually, let me focus on terms which go like p squared. Okay, so there will be terms of order p to the 0. Okay, and then there will be terms of order p to the 4th. Sorry, p squared. Okay, so there will be the one loop contribution, which we just calculated. But then, okay, there will be the contribution from the second diagram. Now, the second diagram you can make, you can check easily that it's finite. Okay, again, once you focus on p square, the p square term in the Taylor expansion. So this again is finite. There is no divergence. Okay. So when you do the calculation, you find that the two loop term gives you a relative correction which goes like lambda over 16 pi square, and then there is a log. So there is a log, but it's a log of ratio scales. So it's m psi over m phi. Okay, with a coefficient here. Okay, some coefficient which of course requires calculation of the diagrams in order to be extracted. Okay, plus p to the 4th. So here is the way in which this log arises, because the diagram is finite. Okay, so there is no mu around. There are two scales, the mass of psi and the mass of phi, and you get these. Okay. Now, at the level of the effective field theory, at this point, you need, in order to capture this effect, you need to insert also the effective vertex at one loop. Okay, so you have in the effective field theory, you will have the diagrams that we already saw, plus a one loop insertion okay, where this is a standard quartic interaction. And here instead, there is the effective vertex, okay? You see why this captures this, because if you shrink this loop into a point, that's exactly looking like this diagram here, okay? Plus, of course, the cross diagrams, okay? Plus cross. So here, now I don't have time, but here, of course, there will be a divergence. Okay, you will have to renormalize the effective field theory. We will do it tomorrow. But the point is that here certainly there will be no dependence on log of m psi. Okay, so again in the matching, what you will get is a dependence which goes like log of m psi, also okay in the coefficient c. So we will see it tomorrow because now there is no time, but there will be a contribution. Okay, this result written over there will be multiplied by 1 plus orders terms of order lambda over 16 pi square logarithm of m psi over mu. Okay. Because again, there cannot be any dependence on m psi in the matching conditions, okay, which is non-analytic. So there cannot be a log of m phi. So in matching these two expressions, this log of m psi over m phi should transform, no, should give you a log of m psi over mu. Okay. And now you start understanding what's going on, because this big log is split into a log of m phi, actually of mu over m phi in the effective theory. We will see it tomorrow. Okay, and in the matching instead you will have a log of m psi over mu. Okay, so this log, which is potentially big, is split in two terms. Okay, one, okay, in the effective theory between mu and m phi, and the other, okay, which now unfortunately I cannot write, but it is a log of m psi over mu, which again can be made small by choosing mu of order m psi. So at this point, the fact that this is big, okay, turns into a big ratio between mu and m phi. But now it's something which is a problem all contained in effective field theory. And here I can use the normalization group to resum all the logs of this form. And this we will see tomorrow. Okay, so the effective field theory approach solves the problem of the loss of perturbativity due to the appearance of big logs in the full theory. Okay, and it does it in a very efficient way. Okay, I need to stop because there is an important seminar. Okay, so unless there are very urgent questions, I think Giuliano